All right. Hi, everyone. I'm Florent Coq. I'm a physicist at NEST. We're going to start the session. There you go. All right. I'm Florent Coq. I'm a physicist at NEST. I do experiment on superconducting microwave devices, and I will chair the session. I am happy to start with the first speaker, Aurelie Denys from INRIA in Paris. Tell us about qutrit.
So thank you for the introduction, and thank you to the organizers for the organization of this nice workshop and for the invitation as well. So I will be talking about multi-mode bosonic codes, and in particular two codes, the 2T-qutrit and the Clifford qubit, both of which are joint works with my supervisor, Aurelie Denys. So they are based on like two different papers. The first one is a work on 2-mode bosonic qutrit, which we call the 2T-qutrit. And the second one deals with designing multi-mode codes with gates that can be easily implemented. So Victor already gave some motivation as to why we're interested in multi-mode codes. They kind of generalize the concatenation of single mode codes with multi-qubit codes, and they are expected to give better performances. So our goal when designing the 2T-qutrit was to design a good 2-mode code whose logical states can be expressed as a superposition of coherent states taken from finite sets of coherent states. And so the reason why we were interested in that was that first, like both the CAT and the 2T codes are obtained as superpositions of structured sets of coherent states. And in particular for the CAT code, it's also a finite set of coherent states. So that's exactly the kind of codes we are dealing with. And so like the last nice feature was for numerical simulations, as having a finite set of coherent states enables to simplify the set of cross operators that we get for the loss channel. So this being said, we need to choose what kind of constellation, so the finite set of coherent state that we're going to use. And so to do that, we took inspiration from the CAT codes. So the logical states of CAT codes are obtained as superpositions of coherent states lying on a circle in phase space. And so they form this sort of regular polygons in phase space. So, like for 2 modes, we, instead of having 2 dimensions for the 2 quadratures, we have 4 dimensions. And so we wanted to look at a regular 4-dimensional polytope. And so to decide which polytope, we again for the CAT codes, well, these constellations, they correspond to the roots of unity, so like subroots of the complex numbers. And so now if you look at the 2-mode case, we no longer deal with complex numbers, but like some sort of equivalent is quaternions. And so we looked at subroots of the units of the quaternions. And the group we chose to focus on was the binary tetrahedral group, basically because it has like a sufficient number of elements so that it's interesting, but not too many, so that it's still possible to perform numerical simulations. So it has 24 elements, which corresponds to 24 2-mode coherent states, and so that will define, well, the spine of this coherent states will define the space that we are considering. But so like within that space, we want to define a qubit, so choose a subspace of that space. And so to define this qubit, again, we took inspiration from cat codes, and here we'll refer to cat quutrits because the 2T-qutrit is a qutrit, so just easier to directly start with quutrits. So like so the three-legged cat qutrit is defined as the code space is the span of three coherent states, the one in like yellow, blue, and red. And then if you go to the six-legged cat qutrit, like the first logical, well, not logical, but like it's defined as the span of three states. The first one being an equal superposition of like the two blue coherent states, and then the second one the two yellow, yellow coherent states, and then the third one an equal superposition of the two red coherent states. And so every time we see that, so we have like some initial states, and then a copy of that state rotated by some angle, and same thing for the nine-legged cat qutrit. And so like mathematically, well, those copies correspond to subgroups, to like whole sets of subgroup of the units, of the roots of the unit of unity, sorry. And so yeah, basically like each state is defined as a uniform superposition of the coherent states belonging, well, that corresponds to one coset of a subgroup. And so for the 2T-qutrit, it's exactly the same. But so like, you know, the big group is the binary tetrahedral group, and then our subgroup is the group of quaternions, so like with plus minus 1, plus minus I, plus minus j, and plus minus k. And so again, so we have like three copies of this subgroup, so like three cosets of the quaternions within the binary tetrahedral group. And we define a code as the span of the states of three states, each of which corresponds to the uniform superposition of the coherent states from one coset of the quaternion. And so if you look at the polytope that corresponds to the binary tetrahedral group, it corresponds again to like coloring the edges in three different colors, and every time it's like a copy of a polytope that is some, well, I don't know if I can say rotated, but like some sort of like a generalization of rotation to get the same polytope again. And so it is an example of a quantum spherical code as was presented by Victor previously. So the states that I've been talking about so far are not orthogonal, well, except in the limit where the parameter alpha of the amplitude grows. But so we can define an orthonormal basis, basically using the fact that so like the operation that transforms one copy of the group into another corresponds actually to a Gaussian unitary, and the eigenstates of this unitary form an orthonormal basis for code. I just put in the first column the formula for the cat qubits, just to show like how similar they are. It's basically the same equation. And so it means also that we get logical Pauli Z, which corresponds to the operation that takes one copy to the other copy of each small polytope. There's another gate that we are able to obtain as a Gaussian unitary, which is the X12 gate. So the gates exchanging the logical 0 and logical 1 states. And so like for the next paper, so the second part of the talk, that these are the kind of gates we'll be interested in. So know that with define of qutrit, we wanted to look at what kind of performances it can give. And so the figure of merit we chose to like check how good it was at like correcting errors is the entanglement fidelity. So that's the same figure of merit as was introduced by Yang Zheng in his talk as well. And so it corresponds to sending a maximally entangled state, and you send one chef onto like your noisy channel, and you don't do anything with the second half of your state, and then you compute the fidelity between the final state that you obtain after sending this half of the state through your noisy channel, and an optimal recovery operation. And so it quantifies how good your code is as at correcting for the noise channel that you're testing. It has the drawback that you're always considering like the optimal recovery operation, and that doesn't mean like you are able to actually physically perform this recovery operation, but at least it enables to easily compare codes. And so yeah, the noise module that we've been considering was pure loss. Well, we did also some simulations with dephasing, but the beginning was mainly the noise channel. And a nice feature about the entanglement fidelity is that you can, by solving some semi-definite programs, you can really optimize on the recovery and also on the encoding. And so we use that to compare the performance of all code to what could be like what you could obtain by performing some optimization to of the entanglement fidelity onto like the Hilbert state defined by the constellation with the 24 Kirchhoff states. And so what we obtain is that like when the loss strength is small, so when there's not too much loss, the biconvex optimization does not identify better qubits than the 2T-qutrit within this 24-dimensional space, which suggests that it's performing well in that case. Since it's some sort of multi-mode cat code, we also wanted it to compare it with a single mode cat code. And again, we found that for a small loss parameter, the 2T-qutrit performs better than the cat qutrit. But yeah, only when the loss parameter is small. Yeah, I don't have the simulations for dephasing, but well, they are on the paper. There's one figure on the paper for dephasing as well. But yeah, it's like I don't have much to say about it. It's like not too good and not too bad. Okay. So then we also like study the stabilizers of this qutrit. So in particular, there are two different types of stabilizers. The first one are just to like stabilize the full 24-dimensional space. And so this can be done with some gender operators, although they look quite ugly. So well, they're not nice for cat qubit, but at least like theoretically you do get a way to like stabilize the 24 constellation, the 24-dimensional constellation. And then we have like the last three stabilizers corresponds to the actual stabilizer to get the 2T-qutrit within this constellation. And so like they corresponds to quantities that are invariant. So like you can all the states in the qubits have a 0 photon in the first mode 2, and they have a 0 mode 4 photons if you well in total, like if you sum the photons to 2 modes. So that's what is said by the stabilizer as green as well. And then the we have like a third stabilizer that is swap gate, so swapping the 2 modes. And so just as a transition to the second part, we can also like rewrite the states of the 2T-qutrit and well with instead of having like the elements of the group appearing in the states, you can like just take an initial state and then apply some Gaussian unitary in it corresponding to the elements of the group to get like the constellation of different states. And so I've just been rewriting like the states in that way with like the group, the elements of the group now appearing as operations instead of states. But that's kind of the same, but will be useful for the rest. And so yeah, the main thing is like here we've been able to get 2 gates, the logical Z and the logical X12 gates with Gaussian unitaries. And so then like the questions we've been looking at in the second paper is to like kind of do it the other way around. So like given a set of gates, we try to define a code such that all the gates in that set could be implemented by Gaussian unitaries. And so that's a question that is really similar to what has been looked at by Jonathan Gross, but for spin qubits. Note that though, like the 2T-qutrit will not be an example of these codes, as like here. Well, we had a qutrit in 2 modes, whereas like the new codes, the dimension of the qubit is the same as the number of modes. So the answer is that yes, we can find codes for which we have like a particular set of gates that can be implemented with Gaussian unitaries. If you have certain conditions that are satisfied. So since we will only be interested in groups which contain the Pauli X, I've put that as a condition. It's not like really necessary. It's not written like that in the paper, but I think it's fine for the talk. Then so like the main condition is that we require G to be a unitary 1 design. So like T designs corresponds to sets that reproduce like finite sets that reproduce the full unitary gates. And so in particular, it has to like satisfy the equation there, because well, the second part is what you would obtain if you were taking the root U2 instead of that one. Well, UG because it would be. And the final condition is that one. It's just like something you find when you do the proof. No, that's to like well, not, but like these conditions are they are like sufficient conditions. They're not necessary conditions. So in particular, the unitary 1 design. Well, you could also like sometimes it happens that you can have the Gaussian unitary for a group that is not 1 design, but if it is, then you might have it. And so yeah, that's the formula that we get for a code that will satisfies that the Gaussian the gates within the group G can be implemented as Gaussian unitaries. And yeah, since like X has been taken to be part of the group, then you just obtain the logical one by swapping the two nodes. So in particular, so like both the Pauli and the Clifford groups are unitary one design. So like the first example that we took basically as a warm-up is the Pauli group. And so we find that like the logical states can be expressed as products of cat states. So by construction, well, of course, the Pauli operators can be implemented as Gaussian unitaries for that code. But also we are able to find another gate, which is like the CZ gate that can be implemented with a controlled rotation of -1. Well, a controlled rotation between like the second one and the fourth mode. So this is like similar to a similar result as was done for the rotation symmetric codes with like this one out. But so an important thing is that the performance of the codes depends a lot on the initial state that we take. Like here we have like an initial state that are taken to be a coherent state, and the performance of the code really depends on that. So we perform some simulations in the case of the Pauli code. So in particular, like the one I've been showing is like the orange and blue one, and well, depending on what this initial state is, the performance of the code in particular here for loss varies a lot. And then the green code was just to try with like a different version of the Pauli code where you do the phase I as well, but it's performance less. That's right. Okay. And so now we can go on to the Clifford qubit. So the Clifford group is also a unitary one design. And so we can also apply the formula for that code. And so this time, we are, so like in addition to like, we have the Clifford operator, well, the single qubit Clifford operators that are implemented with Gaussian unitaries, well, because of, well, the construction. We also have like this thing with the control rotation that enables to get a CZ gate. And then we have like another control rotation that implements a CS gate. And the good point is that so this CS gate does not belong to a Clifford gate, so it makes a universal gate set. Yeah, and so there are a number of generalizations. So the initial state is not the coherent state. And here I've been like dealing with qubits, but you can do the same with qubits. And also, it doesn't have to be like photonic qubits. You can also like state a more general lemma that also to also get results for quantum codes, and in which case you get transversal gates instead of Gaussian unitaries. And so to conclude, well, we've introduced a methodology to design quantum error correcting codes that have gates that can be implemented with Gaussian unitaries. Yeah, the choice of initial state impacts a lot the error correcting performances. We get a universal gate set in this case of the Clifford code that can be like implemented either with Gaussian unitaries or zero gates. That is not so, but it is that can be done experimentally. But so there are a number of like open questions slash drawbacks. In particular, so regarding the state preparation, because like the code that we define in general are not stabilizer codes. And I think I agree with your comments about like having a drawback between the gates and the stabilizers. And also we haven't looked at like any physical error correction procedure.
Any questions?
Yeah, thank you for that nice talk. I just had a question about the unitary one design comment that you mentioned earlier. You said that it wasn't necessary, but sometimes it's nice to have. Do you have like an example of when not having a unitary one design is like problematic?
So what I was thinking about is like, if for instance you would just take like the group generated by X, then it's not a unitary one design. But then since, well, for instance with by adding more gates, it is, well then of course, well, you can implement it. That's why I'm saying like it's not necessary, but okay.
Any more questions?
So you talked, yeah, okay. So you talked a little bit about 2-qubit gates and how you got these controlled rotations. So are those non-Gaussian 2-qubit gates, or are those also 2-qubit Gaussian operate or 2-mode Gaussian operations?
So like all the 2-qubit gates that we have like are implemented with like control rotations. There's like a quartic Hamiltonian.
Okay.
That answered your question.
Yeah, so is there any possibility or barrier to trying to design these things to also have Gaussian 2-qubit gates? Does that make sense?
Only Gaussian, we don't see can you do the design where you only have Gaussian, or is it impossible?
I don't know.
Last question.
Yeah, it's gonna be hard because these Gaussian gates, they're isometric rotations on the sphere. And to do 2-qubit gates, you basically have 2 spheres to work with, and you need to do some conditional stuff. So conditional on this polytope being here, you need to do something here. And doing something here is already quadratic. Figuring out where this is probably quadratic, some parity measurement, some more general thing. So you need a quartic. Right. And I think this nice observation, I think, holds just more general for quantum spherical codes, because if you just add a bunch of quartic stuff, unless you hit on some crazy discrete subgroup of U whatever on your qubits, you're going to be dense in the logical group. We should talk.
Yeah.
Thanks. Cool work.
All right, let's thank the speaker again.